Hey, all you cool cats and kittens. It's your favorite math teacher here, Miss Stein, to talk to you a little bit about functions of several variables. So let's get into some basics and think about what we know regarding regular functions. So a function in terms of x, if we say f of x, that is a function in terms of x. An example of this might be y equals 4x squared. And what you notice is we have y in terms of only one variable. So now what we're going to discuss, we're going to expand on that. And we're going to say, we might have some function z, and z represents a function of xy. So above we had f of x would be equal to y. Here I have z equals f of x and y. So this is a function of two variables. And an example of this you might have seen before. Think about maybe some area equations. Area equals 1/2 base times height. That's the area of a triangle. So if we wanted to write this using our a function of two variables notation, we might say A equals a function of base times height, B times H, or 1/2 base times height. Furthermore, we could have a function of three variables. I could say W equals a function of X, Y, and Z. All right. So we're going to be starting to deal with functions that have multiple variables in them, several variables. The restrictions of the independent variables, all of these being the independent variables, what we plug in, are going to determine the domain of that output function, right? So the restrictions on the base and height would determine the domain of the area, if that makes sense. So let's do an example first. For this example, we're going to find the domain of this function of two variables, f of xy, equal the natural log of the product of x times y. So we have both an x and a y as independent variables in our functions. There are two ways that we can think about this. Sometimes there are more than two ways, but in this situation, we're going to think about it with a picture, right? So the first way we'll think about this would be with a picture. And when we're dealing with natural logs, what do we know about the domain of natural logs? And what we know is the argument of any log has to be greater than or equal to 0. So that means x times y would need to be greater than or equal to 0. So if we think about this on our coordinate xy plane, where would the x times y values be positive? Now remember, if you're multiplying two numbers to get something that's positive, it would have to be two positives or two negatives. And if we think about the fact that in quadrant 1 and in quadrant 3, both x and y are negative. So that lets me know anywhere in quadrant 1, any point, any x and y point, ordered pair that is living in quadrant 1, that would be suitable inside the domain, as well as any xy ordered pair down here in quadrant 3. Can we include the axes? And the answer would be no, because that would be 0, and you can't take the natural log of 0. So I'm kind of drawing dotted lines here to indicate that we are not touching those boundaries. So it is any ordered pair in the unbounded region of quadrant 1 and quadrant 3. So that would be the picture of what it looks like. And again, saying quadrant 1 and quadrant 3, but not the axes. So the other way we could say this would be with words. And so this would be all ordered pairs in quadrant 1, or get that comma out of there, quadrant 1 or quadrant 3, and not on the axes, where x times y is greater than 0. And I'm looking up here where I said the argument had to be the argument of that product, or the argument of the natural log being the product of xy needs to be greater than or equal to 0. And I need to correct myself there. It needs to be strictly greater. If you went to your calculator and you tried to type in the natural log of 0 or the natural log of any negative number, you're going to get an error, undefined, okay? Because those do not lie in the domain of a natural log. There's a vertical asymptote that you never touch at x equals 0 on that natural log graph. All right, so pointing out that error. So another way we could write this a little more formally, a third way, we could say, well, the domain is any ordered pair xy such that xy is greater than 0. And this would be kind of like the most succinct way for us to say it. So all three, 1, 2, and 3, they all say the same thing, but they're presented differently. They're all going to be acceptable, but you want to be able to A, visualize it, and then B, put it into words. And then we could write it briefly. This is kind of more of our math notation. So let's look at another example. So for our second example in this video, we're going to describe the domain of this function, two variables x and y equal the square root of y minus x squared. Okay, so what do we know? What do we know about domain? Remember, we've got three main rules for domain. Denominators are not allowed to equal 0. The radicand, the argument under an even root, must be greater than or equal to 0. And then if we're dealing with a natural log or common log, any log, the argument of the logarithm, the value which we're taking the logarithm of, that also has to be strictly positive, greater than 0. So here we have an even root. And an even root tells us that y minus x squared needs to be greater than or equal to 0. So let's think about that. That means that y needs to be greater than or equal to x squared. And so what does this look like? This is a parabola, right? And all the y values need to be greater than or equal to x squared. So let's draw our parabola. Y equals x squared looks like this. Because it has an equal to, it's a solid line. We can include the boundary. This is a bounded region. And then the y values that would make this true, we would look at picking some value out here on the outside versus some value on the inside. And if I pick a point, say 0, 5, 5 is greater than or equal to 0 squared. If I pick a point over here, 5, 0, 0 is not greater than or equal to 5 squared. So my solution is everywhere inside this parabola or on the boundary of this parabola. Let me pull in a prettier picture. So what we can check would be that anywhere inside the parabola, located inside that curvature of the parabola, y minus x squared is going to be a positive number. Anywhere on the boundary, y minus x squared would equal 0. And then outside, y minus x squared would be less than 0. We'd get a negative number for that calculation, which means we can't take the square root of a negative number. So if we were going to state our domain, it would be that the domain of this function, the domain of f of xy, is any ordered pair xy such that y minus x squared is greater than or equal to 0, or anywhere inside, above the parabola, and then on the bound. So inside or above, however you want to describe that. The parabola, y equals x squared, or on the boundary. So because we can include the boundary here, this is a bounded region. Let's look at one more example. So for this example, we have a function of three variables, x, y, and z. And again, we need to describe the domain. I don't care about what's in the numerator. The numerator can be any number I want, but I have a denominator. And a couple things I know, the denominator cannot equal 0. I also have an even root, so that radicand, what's under the even root, must be greater than or equal to 0. So we can't have not equal to and equal to simultaneously. So what we are discovering or figuring out here is that 9 minus x squared minus y squared minus z squared, that argument in the denominator under the radical, we know that has to be strictly positive. And if I were to rearrange this, I would end up with, we say negative x squared minus y squared minus z squared is greater than negative 9 dividing by negative 1. We have x squared plus y squared plus z squared is less than positive 9. So if I were to think of this and treat this as though it had an equal sign in it, what would this be the graph of? And you all should recognize from our work in previous sections that this is a sphere of radius 3. 3 squared is 9. So it's a sphere of radius 3. And if those variables have to be less than that sphere of radius 3, that means in words, this is the set of all x, y, and z inside the sphere of radius 3. The sphere, there are no shifts. It's centered at the origin. And because we cannot be equal to, we can't include that boundary. So I'll write that in words. We'll say the set of all x, y, z ordered triples inside the sphere of radius 3 centered at the origin, not on the boundary or the edge of that sphere. And with our succinct, our short math notation, we would say that the domain of F is the set of all x, y, and z such that, it doesn't look like a colon, such that x squared plus y squared plus z squared is less than 9. And so I hope at this point you have a decent idea of how to find the domain for different functions of several variables, 2 or 3, potentially even 4, but we're really going to be dealing with 2 and 3 variables in this unit.